So that was great. So that was great. So it, and as Yoando says, it's a 3-layer system. At the bottom layer, you've got all your Agile teams. And they're traditional 7+or-2 type Agile teams with Scrum Masters and product owners and a development team. But then to scale it, it imposes these layering. And so it makes an argument for about the sort of 50 to 150 people is psychologically about the number of people that someone can get their head around. That's the number of friends you actually know on Facebook, not the 1,000. It's actually the only 100, 150 sort of thing. And so they say that's a social size which is manageable. So that 50 to 150 people are encapsulated in something they call an Agile release train. So this is sort of Twiddle's 10 Agile teams, and then there's an Agile management team that's running the train. And this is where you have the DevOps grouping. You have, workflow being fed down into these teams. You actually have 3 people who are effectively running the train. There's a release train engineer, which is akin to the Scrum Master, who's responsible for processes. The product management, it's akin to the product owner, who's basically the customer representative, and the system architecture engineer, which is equivalent to the development team, who maintains architectural coherence. And they basically maintain this continuous delivery pipeline. All the teams are working on these 2-week sprint cycles traditionally, but you all come together every 3 months for something called PI planning, where you basically stop the train, everyone's finished, doesn't do any development for a bit, you have a week of planning, and you might move functionality from one Agile team to another. You make commitments for the next 3 months, and then go off, and the Agile teams then work independently, or largely independently. And then there's the top layer for something which is larger than that, which is called the solution layer. And this is where system engineering really comes in. And here's what the system engineering model that you see in large developments comes in. But the point here is that, as again one day said, you don't start off with a completely fixed set of requirements and ICDs and then work to it forever. You accept that you build up the fixed component of the solution intent over time. And so you start off not quite knowing what you're doing and accepting that. And then towards the end, everything's fixed and there's very little variable stuff. So now we've got the scaled Agile framework going, so now we've socialised it. Everyone's basically signed up to it. And now we've got these roles and processes and things, we can start thinking about ways it's going to work within our organisation. And as I said, there's clearly information flow, and it's called communities of practice, where people of like mind work together. So here there's a technical community of practice consisting of the solution architect, the system architects at the... So this is the release train level, this is the solution level, this is the actual team level. So down this right-hand side, there's the technical people maintaining the architectural coherence. Here, there's the process delivery people who are basically focused on improving the processes, improving the workflow, the flow of value through the system. Here's the content, consisting of the product owners who are breaking your big epics down into features, into user stories as the things go down. And of course, there's the customer representative who are feeding in, the customers out here and the owners who are feeding in to these product managers, solution managers and product owners who are the effectively customer representatives on the team. And then that flows through the feature teams, out through the system team who are building the DevOps system, and then into traditional integration and verification. Then finally, one thing about Agile, and the whole point about this is, unfortunately, maybe for some people, you have to all sign up to essentially a heartbeat. And the reason is you're synchronising the whole development across these times. The reason you're doing this is so that you can actually align the communication pathways. So you're not calling whenever you're calling meetings at random times, the communication happens at particular times, at the end of every 2 weeks, then at the 3-month intervals. So you can align up these meetings so you know how the communication flow is going through the system, starting with the daily scrums, and then your sprint planning meetings, and then you get the whole project together, even the dish manufacturers, in this program increment meeting. So I'm just run just slightly over time, I apologise for that, but in conclusion, this is what I want you to take away. Personally, I think the Agile Manifesto is a good anchor, but you've got to remember that the values on the right are still important, particularly in a big project. You've got to remember that software architecture is driven by qualities more than every little detailed functional requirement. And I think the software processes need to match your software qualities. And they've come a long way in 20 years. And I think this is something I didn't really mention. If you've got a better software to write, which may be a device driver, which is sandwiched in between, a piece of hardware and an operating system layer, and it's completely defined, and so there's no need for agility, then a non-agile process for developing it is probably appropriate. Alternatively, if you've got potentially a lot of flux in your system, then that's when you need an agile process. And I think in a project like the SKA, there are so many unknowns that we have to maintain that bit of agility. You need good foundations, people and infrastructure. You need the other disciplines. You've got to acknowledge and cultivate them. I've been to a number of sites where basically system engineering and software engineering don't really talk to each other. They just don't understand each other. And finally, this point that I've made a couple of times, that standards and industry best practices are great for convincing your stakeholders of the merits of your arguments. Again, I hear people saying, management just won't listen to me. If you say, this is the world's best practice on how to do something, and then management doesn't listen to you, then they have a problem. And that's also useful for getting all your stakeholders on the same language. So anyway, thank you all for bearing with me. Sorry I ran a bit over time. Any questions? Thank you.
Thank you, Nick, for your presentation. I was wondering, given the quality properties described in the ISO 20010 standard that you just showed us, which ones do you believe are the most crucial for the success of a project like SKA? Because I saw like 8 categories.
Well, I think it depends. It depends whereabouts you're focusing on. But I think one thing that's important to know is that, SKA is a 50-year time cycle. And so one of the important ones, I'd say, is modifiability. Because this is another reason why your requirements aren't so important. Because your software has to be appropriate for the requirements that are coming down in 5, 10 years' time after day one. So your software has to be, I'm thinking particularly in the online system, there has to be a, science is a volatile subject, and you have to be able to modify your software to cater for the new demands of science. In our science data processing, performance is clearly the be-all and the end-all. So that's an obvious one. So it does depend a bit on where in the system you're talking about. But, there's certainly a number of things which I've seen, other organisations, if they'd sat down and thought about it, they would have realised how important modifiability is. And they've ended up with a system which is, got single point failures, and, it's all a bit too uniform, and it's not, separation of concerns is so important, yeah.
And David?
So you're saying that software architecture is driven more by qualities and requirements. Personally, I agree. But for us, the projects are driven by the requirements. So they drive the subsidies. So at some point, when you're downscaling, because you can't make everything, the qualities tend to suffer, and then you may end up with an unusable system. So do you have any advice on that?
Well, yeah, I think there's a dialogue to be had there, because one of the points about Agile is you've got to get people to admit that the way they've done it hasn't worked. You see what I mean? Because if you look at projects with their long list of requirements, when they get to day one, what they find is they haven't met quite a lot of them, and a number of them are irrelevant. So you've got to have some. There's no substitute for very good product owners who actually know how to prioritise things. So if you've got the right quality software, you will be able to meet the requirements. You just haven't got there yet. If the quality isn't there, you might have problems meeting the requirements.
Okay, thanks.
Yeah.
Let's thank our speaker again. The next presentation will be given by Anastasia Leite from Caltech, and she's going to present a cloud-based solution for software test and integration at the TMT.
All right, can you hear me? I can hear me. Good morning, my name is Anastasia Leite. I'm here on behalf of a team from IPAC at Caltech to talk about how we're building a cloud-based software test and integration lab for the 30-meter telescope. You guys are a lot of astronomers, so most of you might have already heard of the very large telescope that is coming. That's just an artist's rendering of what it will eventually look like on the summit of Mauna Kea. But what's interesting from a software perspective, so to me specifically, is that it's an international partnership. TMT Project has members all around the world, all around the US, from Hawaii, California, Colorado, on through Canada, China, India, Japan. They do a lot of teleconferencing. There's people working all hours of the day. And so they wanted a solution for their software testing and integration that would also be global, that would be portable, that would be cloud-based. And so the TMT Software Test and Integration Lab, or STIL, is just that collection of tools, services, and staff to support TMT's software development processes. This table shows the key components of the STIL. For a nice global overview of the whole set of tools, I definitely recommend you guys wander downstairs to poster 130. My colleague Wendy Burt has a really lovely poster down there. Today, I'm going to be mainly focusing on the components that relate specifically to the build and test environments that we set up for TMT software teams to use. And these are just little virtual machines that we can spin up in the cloud, and they can then hook into all of their GitHub repositories and other tools, and constantly be testing and integrating their software, making sure nobody's breaking everybody else's stuff. So that uses Amazon Web Services, which I think is becoming more and more popular with all of us. Anybody in the room using AWS already? Yep. We prepare all of those little BTEs using Ansible playbooks, and that is a file-driven, configuration file-driven system for deploying and configuring servers. For continuous integration, we're using an automation server called Jenkins. Some of you have probably heard of that too. Any Jenkins users? Great. We use that ourselves as still admins, and it also comes as the front end for every BTE that we launch for the software teams to use. Each BTE, along with that Jenkins layer for the developers to interface with, comes with all the compilers, code checkers, formatting tools that the TMT project uses. And they can be configured to talk back to the communication tools that the whole project uses, which are Slack. That's one of their primary methods for real-time communication. Again, the whole TMT project, not just the still. And GitHub is where the TMT code repos live, and it's also used for doing code review processes. So one other idea behind this whole thing being cloud-based is also that it should be accessible very easily and from anywhere. So you'll note that all of these tools in the end, and accessing the BTEs, can be done with just a web client. Nobody actually ever needs, once we've got things up and running, to be able to set up firewalls on their, VPNs on their phone to get through weird firewalls or log into special things. It can all just be done with a browser if you need. At the bottom, I'll just mention that we are using the Atlassian services for other communication and issue planning tools. And again, check out P130 for some more information on that. So today, like I said, I'm talking mostly about those BTEs that we build. We keep it it's very reproducible from the management end. We want it to be easy for us to spin up new ones whenever they're requested. So like I said, the configuration is all handled via Ansible playbooks, which we store in a still specific repository that is part of the overall TMT projects repository. So we as administrators can deploy new BTEs by logging into that Jenkins instance on our own server, also in the cloud. And that is itself reproducible via playbooks that are stored in the cloud. So if, for instance, one of us deleted the wrong instance in our Amazon Web Services console while we were testing this whole process, it turns out that yes, in fact, we can recreate it as planned using those Ansible playbooks. And by the way, you can also clone your images in Amazon so that that is not an issue. Once they're up and running, we manage and monitor them using that AWS console so we can keep an eye on usage and costs. From the user's perspective, they request a new BTE using our help desk, and they get back a link to log into Jenkins. It's going to come with a few sample projects that they can use to configure their own, and they're going to hook it up to their own Git repositories, and it can be set to communicate back to their Slack channels that they're monitoring to see how the tests are going and how the nightly builds are going. We do recommend that they set things up to run whenever things are pushed to Git, especially for the like the master branch stuff. For lower development level things, if they want to just have scheduled tests or run them by hand, those are also options in Jenkins. And because all that stuff is handled after we've handed over the BTEs, right, the users can then go in and make edits. Now it's drifted away from that base installation that was reproducible. So we make sure to back up all the configuration files inside that Jenkins install every night so that, in fact, the final state of that BTE is still reproducible. If it gets damaged beyond repair, if it gets blown away for any reason, we can always put it back to the state that those users had it in. I just have a slightly more visual version of that workflow to help you guys visualize what happens. I'm one of the blue guys on the left, so we update our own GitHub repo with the Ansible playbooks that control the BTEs. We log into our Jenkins server, hit a button, it's almost one click, and that's going to retrieve the latest playbooks from the GitHub repo and launch whatever BTEs we request it to. It also sends a notification to our own still Slack, so we can see, yes, that worked, and here is the URL that we should now send to the user along with their login credentials. The developers can then access the BTE and set it up against their own GitHub repos, their own Slack channels. And like I mentioned before, they can either run those projects by hand or, preferably, set it up so that whenever they do commit to that Git repo, it automatically launches whatever tests and build instructions they want to verify, and again, outputs to their own Slack channels that they instantly can see, whoa, I should not have pushed that change, I better fix that right now, or yes, everything is going fine. I've just got a few screenshots to give you a more concrete view of what that looks like for those of you who haven't already used these tools. This is kind of what we would see when we log in as an admin. We've got a few options to try launching BTEs. And we basically can enter just a few tags that will get passed through to Amazon. Amazon has a very robust API with Ansible, so you can pretty much do anything that you would do through the console. And we also have a few options to override things like amount of disk space available to those things, size of the machine. If some teams need more CPU or more memory, we can make that happen. And then once they're up and running, we have our monitor in Amazon console where we can just keep an eye on things, stop BTEs when a team is done with them. We don't want them running all the time and running up costs if they're not needed. From the users, the software developer's perspective, again, they can basically just grab that GitHub URL and plug it into the Jenkins configuration. And at its simplest, Jenkins just grabs code and then runs whatever commands you tell it to run. You could build now, hit that button, and you'll get both console output in Jenkins, which you can capture and send back to those Slack channels. And you can do 100 other things. Jenkins is integrated with a lot of different tools. So if Slack is not your communication method of choice, there are a lot of other options. So in summary, we are finding that this particular combination of Amazon, GitHub, Ansible, and Jenkins is a really powerful, really nice system for automating deployment of these little virtual machines or bigger virtual machines. It's helping us to control costs with Amazon's pay-as-you-go approach. But the overall architecture that we've done here doesn't depend on these specific services, right? If you guys are already using Bamboo instead of Jenkins, you could do something very similar, but with that tool instead. Going completely cloud-based on this has been a really interesting experience. It's great that it doesn't require any local infrastructure. We're not adding more stuff to our data center, and that it's accessible everywhere. But of course, the one gotcha is that you do still have to be aware of when you may not have direct control over versions of software that you're using. We had a good example this summer with all the Atlassian products because we are using everything in the cloud, and we prepared all of our demonstrations based on how that looked at one particular time, and a week later got a little surprise upgrade, which was good. It was a wonderful upgrade, but again, you are giving up some control if you do that sort of thing. So you don't get to sort of abdicate responsibility entirely in terms of version control and configuration management. You still have to be thinking about those things. And I would definitely recommend sticking to the stable release versions of stuff like Jenkins when possible. It's also helping us a lot to encourage developers to actually use these tools, right? They're no use to anybody if they are just available, but nobody actually implements them. And we found that by keeping it as simple as possible from the developer's end, and by providing augmented documentation, so not just pointing them to, oh yeah, go look at the GitHub documentation, oh yeah, go look at the Slack docs. We want to tell them, hey, here's how you guys should be using this for this project. Here's a few basic 1, 2, 3 steps. So as mentioned in the previous talk, actually, it is very important to remember those other disciplines, such as your document writers, and get them on board to help keep this as simple as possible. And that is actually all I have today. So thank you very much for your time. Questions time, I guess.
Yes, one.
Oh.
We have only one microphone, okay, so you can.
Okay, thanks for the presentation. Actually, I have 2 questions. The first one is, you mentioned that you are using GitHub as repository, but on the other hand, you are also a lot of Atlassian tool for the development, for controlling the software project.
What was the first part of that question? We're using...
Yeah, you are using GitHub, but you are using Atlassian tool for the rest. So why you didn't choose, for example, the Bitbucket solution, which is an Atlassian tool and you can connect everything?
Or why are we using Slack instead of, I think, HipChat or Stride, the new Atlassian tool? So there was actually, I think, a 3-month-long selection process that happened last year with various stakeholders all across the TMT project. Some tools were selected because the TMT project, which had started before we came into it, were already using them. And I'm not sure if GitHub was one of those. I think it may have been. I know they were already using Slack, and that's why we went with that. So I don't know specifically, but I think I have some documentation that had more description of why we made particular choices that I could certainly look into. But yeah, I mean, there's a lot of stuff out there right now, and everything that we chose does integrate nicely with each other, even in the cases where it's not the same vendor. So it's an interesting time to be trying out these tools.
Okay, thanks.
Is that the first question or the second question?
The second one is related because you use the cloud for hosting your virtual service. But you compared there was a comparison between having all this infrastructure in-house and using the cloud. Because I think cost is one of the
Absolutely. I mean, I think a large part of doing it this way was to cut down on costs. The cost of running a handful of these Amazon machines was coming to a couple $100s a year. I mean, it's something really small. Now, as you run larger machines or for more time, you can get in some trouble if you don't keep an eye on that. But I think it's still well under the cost of the FTEs and overhead for employing people like me, right? I'm a system administrator at Caltech, so I do have an interest in keeping my job. But also we have enough computers in our data center, and it's nice to have some that are a little bit outside that direct control and that we know Amazon is taking care of. So it is, as we're running it, it is very cost efficient, yeah.
Okay, thanks.
Luis?
So your BTEs, how long are they typically running?
They could run forever. If you have a project that just wants to run little nightly builds and it doesn't ever mess up the BTE, I would recommend probably eventually we would want to shut it down and bring up one that has all the latest changes that we've made.
Yeah, but that is a meta problem then, because you may change the BTEs themselves, right?
Yeah. So we are still just kind of ramping up, so we've just got a couple of developer teams using these so far. So far the answer to that question is 3 months. But they are designed to be basically fired up when needed and then shut off and destroyed once they're done with them, and then we'll fire up another one. So I think we'll see different classes of those, totally based on the specific software project and what their needs are.
Okay, thank you. Let's thank Anastasia again.
Thanks very much, guys. Water bottle.
And our next speaker is Keith Shortridge from KNV. He will talk about instrument simulation software for the AAO.
No, que está bloqueado.
Right one. Good. Okay. Are we off? Oh, good. Right, good morning, everybody. So this talk is a little bit more small scale and nitty-gritty. Hardware simulation. How do we do it? More to the point, why do we do it? And to try and explain that, I want to talk about something that's really interesting, which is project scheduling. Right? Knew you'd agree. Everybody stay, bar the doors. Here's the schedule for a typical astronomical instrument. You'll recognize this. You build the mechanical bits, you install the optical bits, you wire in the electronics. While you're doing that, somebody's written the software because that's, easy. You put them all together, brief testing, call it commissioned, go on to observing. Right, done. Next instrument, please.
Now, in practice, of course, we know that software, if you want to develop software properly, agilely, it's much better to have an iterative design, implement, test, evaluate, rethink, repeat sequence. But if what you're writing is control software for hardware, that test part of that needs the hardware available, which means that in practice, it happens not there, but there's this additional step which is basically get the software working. And that's also known, of course, as blame the software for the delay in the project. Now, being blamed is not much fun, and we want software by development to be fun, right? Because if it's not fun, it's merely well paid, and now actually we really need it to be fun, okay? So to get around this, what you want to do is you need to test the software with the hardware, but you need to do it early on, and you need to do it when you don't have the hardware. So how do you do that? Well, I'm sure you can see where this is going. What you do is you simulate the hardware in software. But if you're going to do that well enough to thoroughly test the software, you need an almost perfect simulation of your hardware. Now that's ambitious, but it's what we've been trying to do at AAO recently actually about the last 10 years. The first system we did this for was the new control system for the AAT 3.9 meter telescope. Now, you'll realize that this is not a new piece of hardware. It's there, it's working, it's well known, but it's also an operational telescope, it's in constant use. It's actually not available to the software team for testing. So in order to test this, we realized that we actually did need to simulate the telescope completely and obviously really accurately. So that's what we've been doing. Now, to talk about simulation in detail, the important point is that if you're simulating, there's always a point where you have to ask, am I simulating? If so, I do this. If not, I do that. There's a simulation break in the software. And the question is, where in the software do you put that? So here's a typical bit of a telescope control system. There's a module here that, say, handles a telescope axis. It gets a command that says move to somewhere. It may calculate, say, a voltage for a motor. It writes that voltage to the motor through a write call to a driver, passes it down to the telescope interface electronics. The telescope moves. Now, where do you put that simulation break? Where do you do that test? Well, you could put it right at the top of this axis control block of software. If simulating, say, okay, did it fine, and if not, you go on and do it properly with the real hardware. Now, that's actually fine. It will test out the higher level control bit, but it leaves all the rest of it untested. And that bit that's untested may actually be quite complicated. It might, for instance, on the AAT, we close the servo loops in software. So that bit down there that's untested in this case is actually doing the reading the encoders, calculating, tweaking the voltages. That's actually the tricky stuff, and that's what you really want to be testing. So that's not a very good solution. So here's obvious take-home point number one from this talk. You have to introduce simulation somewhere, but any code lower down doesn't get tested. And what that tells you is that if you want to test your code thoroughly, then you need to put that break as low down as possible. So how low can you go? Well, about as low down as you can go without actually being in the hardware itself, and you don't have that, is the driver. So we could put the simulation break in the driver. Now, only the truly foolish mess with drivers. They're complicated, but more to the point, they're also not portable. And I want to be able to run this on my Mac laptop in simulation, but as well as on the Linux machine that we actually deploy it to. So we're not going to mess with the driver itself, but what we do is we introduce a very thin layer called a driver interface, and that's where we have the simulation break. So the driver interface looks like a driver. It has open, close, write, read calls. And there's the simulation break. If you're not simulating, these calls just go straight to the real driver. If you are simulating in our system, they go down into this thing called an X-Wing driver. X-Wing is the AAO's subsystem that lets you emulate drivers, basically. If you go down to here, your write call goes down through a lower layer of the system and out to a Unix pipe. And I'll show you where that goes in a moment, but in case anybody's wondering, did anybody spot where the name comes from? If you aren't using the X-Wing, you're using the telescope interface electronics, which of course is TIE, and the opposite of TIE is X-Wing. Everybody knows that, right? So, having got that embarrassing choice of name out of the way, let's move. What's at the other end of that Unix pipe is a single telescope simulator task, which has which has an X-Wing layer at the bottom, which takes all those calls apart and passes them on to the actual telescope simulator. So the actual telescope simulator is seeing calls like somebody wrote this to this device, somebody's reading this from this device, and it simulates them all at that level. So what you get there, every single low-level I/O operation that would normally go to the hardware interfaces is now going to that simulator task. And it simulates that as accurately as possible. So obvious take-home point number 2, the simulation needs to be perfect. Every I/O bit, every analog value, every mechanism. Also, having it all in that one task means that it's coherent. Even if you have multiple control tasks running, they're all going to see the same simulated telescope. You get a coherent picture of what the telescope's doing. Now, making this as perfect and as detailed as possible as this is really hard work, but it's worth it. The first time this control system saw the actual hardware was at night on the mountain. We asked it to move to a standard star. It slewed over to a standard star and settled on it, and it was spot on in DEC. It was 5 arc seconds out in RA. Now, that's not perfect, but it's pretty encouraging. So, since then, if you can do it with a telescope, you can do it with any instrument, and that's what we've been doing for later instruments like the AAO's Hermes spectrograph. The Hermes spectrograph is interesting because by now all AAO instruments are using CAN bus interfaces. You've used CAN bus, almost every one of you has used CAN bus because your car uses CAN bus. Every bit of your car is talking to every other bit of your car along a serial line, passing 8-byte CAN bus messages using a really complicated protocol that you really don't want to know anything about at all. And the AAO instruments are now pretty much the same. So the question is here, where do you put that simulation break in a system like this? Now you could put it here, intercepting those CAN open 8-byte messages and sending them to a simulator task, but no sane person is going to do that because then you're going to have to, your simulator is going to have to reverse engineer those 8-byte messages, the entire CAN bus protocol, the CAN open protocol. That's a nightmare. You don't want to do that. Here's 1.5 milliseconds of the dialogue between when a CAN bus amplifier starts up. You don't need to follow any of this other than to note that there's an awful lot of it. This is just a bit of it, and it's awfully complicated. You don't want to know about it. But, so you could put it here and just I should say CAN bus is complicated. You don't want to be writing and it's a known system. So we brought in a commercial library to handle that called CML. It works very nicely. You could intercept those commands there and send them to the simulator task. You could emulate CML, but we didn't want to do that. And you might say, why don't you want to emulate CML? It means CML doesn't get tested. And you might say, why does it matter if CML doesn't? It's a proprietary system. Aren't software warranties worth anything then? But what we were really worried about was that this highly multi-threaded system library might not play well with the drama instrumentation environment that we use. And if it wasn't going to, we needed to know really early on. So what we did, in fact, was we did what no sane person would do, and we bit the bullet, and we actually wrote a complete reverse-engineered CAN-open simulator to sit on top of the X-Wing layer. We now simulate everything at that sort of level. It's complicated, but it works. Very hard work, but it works. Let me just quickly show you. This is what Hermes really looks like. Here's an interesting thing. It's got an emergency stop button. Actually, it's got lots of emergency stop buttons. You want to test how the software reacts when somebody presses that. That means the hardware's got one of these. The simulator needs one of these. How do you give a simulator a stop button? Well, you give it a GUI. And in fact, you give it lots of things. So it's got a stop button. It's got all sorts of environmental controls as well. I can open the door of the spectrograph room and check that the interlocks work properly. I can play around. I can flood the whole spectrograph room with hazardous gas and see how the software reacts to that. Now, obviously, there's other ways of testing how the software reacts to flooding the room with hazardous gas, but most of them involve flooding the room with hazardous gas, and you don't really want to do that. So simulating it is way better. What's next? So there you are, obvious take-home point 3. The simulator needs a GUI so that external events can be simulated. And the nice thing about having a GUI is it can also display the internals of the instrument, and it can warn of software errors. And this is my last point. The GUI, the simulator, knows how you ought to run it. One quick example, Hermes has mechanisms with optical encoders. It's an optical spectrograph. You might wonder why it has optical encoders in it. I did, but it does. They have to be turned off during observing. Servo amplifiers don't like having their encoders turned off while they're servoing. So there's a complicated sequence you have to follow, disabling, enabling things, saving and restoring values. Our CAN bus simulator knows this sequence, and if you get it wrong, you get a warning down here in the simulator GUI saying, you're programming me wrong. If you do that with the real hardware, it just goes to the wrong place. So it's much, much better to do it with the simulator. You will never want to use real hardware again. And I'll just leave this side up and see if anybody has any questions. Yeah.
You're very lucky to have a telescope that you've used before and you know how to simulate it. What do you do if you've got something more complicated? So I'm building PFS, big fiber spectrograph on Subaru, where we have to close the loop on the positioners by imaging them from down in CAS. And then there's bunches of nasty code. We don't know how the fiber collisions work. So that's a bunch of instrument software. I'm not talking about what the spectra look like, what I actually work on. But how far down that system would you try to simulate it? And how much would you say, I can get the plumbing done right, but wait till we get real data, engineering data, before I actually simulate further down?
Well, you're certainly right. We were very lucky with the telescope. It's a well-known instrument. We know all its foibles, all its quirks. That 5 arc-second RA error was a gear correction that we knew about, but it turned out that the new system was calculating but not applying. So we did know that very well. But other instruments, we've done this with fiber positioning systems. We've simulated the movement of the star bugs in our Taipan positioner. We've done that at that level so that the control software for the bugs themselves can be tested beforehand. So, I mean, at that level, you're really just providing something that, okay, yes, you're right. If you don't know how it's going to work, you don't know, you have to simulate the foibles of your hardware, and you don't find those out until you've got the hardware there. But you talk to the engineers, one thing about this is that if you write a simulator for something, it gets you talking to the engineers much more, which is actually a good thing. You may find out the things that are likely to go wrong with it. You can probably get an accurate simulation. You sit in on the tests and you see what is going wrong. You keep iterating your simulator so that when you find out something about the real hardware, you put that in the simulator. And of course, as you iterate towards that, once you've finally got the whole thing going, you've got a simulator that's emulating it all perfectly, well, reasonably perfectly. And the nice thing is, which I think you're going to hear more about next, is you can use that simulator during the operational phases. You've got an accurate simulated instrument that you can use to look for bugs in the software higher up. I mean, your point is perfectly valid, but it's still a useful thing to have that simulator there.
One more question here? Maybe you.
Yeah.
Okay, Jeff.
Sorry. And thanks for the talk. And we found this very useful when we were doing with Alma. But my question is, when you're budgeting for a project, how much does this inflate your cost profile?
Yes. What you say is, this is part of the software development. You have to take it on board, but overall it's probably going to help, because what it's going to mean is that you're going to have more of the software testing, more of the bug finding, fixing done in peace and quiet, down in the offices on your laptop at home, rather than when it's really critical up at the telescope using night time. I think you can make a fairly good case that it's worthwhile spending that investing that effort in producing something like that early on. It also keeps your software team doing something productive early on in the stages while the hardware's arriving. And it also means, and even when the hardware arrives, it's not actually accessible to the software team because the hardware people are still finding out how to make it work. So it's actually quite hard to get at hardware most of the time. So I think it's a worthwhile investment, and you can make the case for it. It obviously isn't free.
Yeah, sorry, I wasn't arguing that it's not worth it. I was just asking for, when you go to your management, what's the number you give them? Is it a factor of 2? Is it a factor of 1.5? Or do you not calculate it?
I don't remember calculating it.
Okay, if there is only one more question, then I'll take it.
Thank you for that. Have you looked into using mocking frameworks, and if you have, do you use them, or did you reject them, and why?
No, we didn't look into that at all, I'm afraid. So I don't have an answer to that question. Incidentally, I'll dob him in, Tony Farrell, who's head of AAO software and has responsible for things like budget and planning. If you want to talk about estimates and things, he's probably a better person than I am for that.
Okay, thank you, Kish.
Right.
I would just like to ask, is Thomas Romain in the room? Not okay. So our next speaker is going to be Su-Cheng Shen, and from Alma. He's going to give a talk on the evolution of the simulation environment in the Alma Observatory. Maybe.
Sandy? Hello. Ese. Gracias. Hello, everybody. So my name is Su-Cheng Shen. I'm one of the software operation manager. I'm also the testing manager in Alma. For the operation group, we have around 16 engineers, and the testing side, we have around 20 software testers. And of course, not all of them are full-time dedicated for testing, but the people are around 20. So before we talk about how to test Alma software, I will give you some overview of what Alma software is. So Alma works in terms of cycles. Every cycle, the duration of every cycle is 1 year. So currently we are running the cycle 5. The cycle starts with the proposal submission, and then we have proposal selection. Then those selected proposals are scheduled, and the observation is done at the observatory. Then those raw data has passed through several quality control until it reaches to the pipeline. So essentially, there are two big groups of software. On one side, we have a lot of we call offline application, which is a more database-driven application, Java web-based application, and another important part is the control-related application. And those software interface with the hardware, has all the challenging with the real-time control, and that's the focus of this talk. So in terms of architecture, so we have the environment that we use to run the Alma software is a cluster of server, which interface with the 66 antennas, and the correlator and other photonic reference, and so on. So in order to run this, the software, we have an environment which in total has 133 servers. That includes the real-time servers, the cluster servers. And in terms of network, we are running on top of Cisco 6500 core switches and 3750 access switches. This has been replaced with a newer version of Nexus switches. And in terms of network address, we are using Class C routing schema. So, but this environment, sorry. This environment is for the main array after we complete the array in operation. But during the AIV period, so when we are doing the commissioning, we use the same environment with a smaller number of servers. Okay, we use and abuse this environment in order to set up several parallel environments in order to commission all the hardware we have been receiving. For example, we are doing the optical pointing, holography, in order to test the dish accuracy, radio pointing, and then at the end, we integrate that antenna in the main array. So during that period, we have a lot of, we reach the number of 12 environments that we are supporting all the commission period. But when we started with the operation, the priority have changed. In the commissioning phase, there are a lot of hardware available for all kinds of software testing that we need. But when we started with the operation, every single piece of hardware has to be dedicated for the scientific observation. So it's very hard to get technical time just for software testing. But the Alma software is still changing over every cycle. So. And every month, we are receiving a new version of software that we need to test and verify and decide if we go for production or not. So the first approach we did is using a hardware approach. So in the right, you have a schematic of the hardware which is involved in the array. So the green boxes are the servers. The yellow one are the real-time computer, and the black one are the hardware that we have in Alma. So what we decided using the VRF, the virtual routing and forwarding concept, which allow us to isolate some piece of hardware that we are interested in order to form a smaller interferometer. The virtual routing and forwarding allow you to have different domain in your hardware, in your switches, and have the same network schema with the same network addresses, but they don't see each other. So we just need to add another set of cluster of server, and that allow us to run a different version of Alma software we can do the testing and do all kinds of verification that we want. That was very useful, but we are testing just a small number of antennas, for example, and so any test related to scalability or performance cannot be done here. So we went to another approach, so we're using simulation. As we mentioned in the previous talk, we did the same. We just replaced the driver layer with simulators. But the consequence is we don't test anything related to the driver, not communication with the hardware. The advantage of this approach, this allows us to create all the number of instances of the simulator that we want, and that allow us to do all kinds of testing related to the scalability and performance aspect. So, and this environment, we cannot afford to repeat the same production environment because it's too costly. So we use an approach which worked very well for us. We consolidate the number of servers. For example, for the antenna, we have 66 real-time computers. Those can be consolidated with a factor of 8 in 8 blade server, more powerful 8 blade server. So repeating the same exercise, we managed to reduce the number of servers from 135 to around 32 servers. It's still expensive, but it's more affordable. So this environment has been very, very useful for regression tests, scalability tests, and performance aspects. Once we have done these two approaches, we say, why don't we just combine both of these approaches? So we reach to this architecture, which is a hybrid concept. So we combine the real-time and hardware in the loop concept plus the no real-time simulation. So with a single test, a single run of tests, we can achieve 2 dimensions. One is we can generate all kind of loads, the CPU load, the memory consumption, and network traffic in one dimension. And another dimension, we can test all layers of software, even the communication traffic with the hardware. In Alma, we are using CAN bus. So we could generate the same amount of CAN bus, so we exercise every layer of Alma software. That would give us more confidence about the stability of our software before going to production. In order to establish this environment, what we need is additional hardware. So we are requesting budget to have another quadrant. Remember the Alma, the baseline correlator of Alma, there are 4 quadrants. But we just need another quadrant that would be enough to demonstrate, to exercise that layer of software. The rest of them will be combined through no real-time simulation. So this is project, which is the project is still ongoing, and we can go even further. So instead of using the real hardware or similar hardware, we can use emulators. We can create an emulator and generate faulty conditions and check what's the reaction of the software upon this kind of failure. And the idea is we should have a very big log message or alarm telling the operator this is a hardware problem, another software problem that's happening, which usually happen in the observatory. Everybody thinks that problem is related to software, but it's not very clear to understand the problem is related to the hardware. So this work is still ongoing. And in conclusion, so we exercise with different simulation approaches. And now we are working in this hybrid mode, and will be more efficient because we don't need to repeat the same test in different environments. The simulation and the different simulation environment that we had has been very useful to process this incremental release management that we have in the last 3 years. We believe that the hybrid approach will really improve our test coverage in the future. So This graph is for people who is working in testing. If they don't get the money or the budget for their project or for the infrastructure, show this graph to to boss. And I think everybody knows the sooner we detect a bug, it's cheaper to solve it. Yeah? And when we detect, if the bug could be detected only on production, that's really, really, really expensive. And there's something else that the money cannot buy is the credibility of your team. Once you have so many failures, it's very difficult to keep working because nobody trusts your work. Okay, thank you very much.
Any question? I do have one. Could you comment a bit on what are the main differences you observe between the simulation environment and the real environment? What are the main problems that you could not address with the simulation?
Well, the simulation that we have just overload the driver layer. So the simulation, the simulator that we have the quality of the simulation depends the subsystem the effort the subsystem have invested in that simulator. So as the previous talk, if you just return OK, it's a very simple simulation. It won't add any more value. But there's some of team has invested a lot in a simulator. So it's quite similar to the hardware, but you can never replace the communication with the real hardware. And most of the problem, once the project has been entered to the operation, everything is mature. Most of the problem is not in the component itself; it's mostly in the interaction with the other component. So that you cannot simulate.
So if there is no more question, let's thank our speaker again.
Thank you.
And so after this final talk, there will be the first lighting talk of the session by Romain Thomas. And now our next speaker is Reinhard Anuschik from ISO, and he will present deep news data cubes for the community.
Okay, good morning, everyone. Now let's change focus a bit from simulations to real data. My talk is about applying the Muse pipeline to the data beyond its original purpose. My name is Reinhard Anuschik. I'm working at the Data Processing and Quality Control Group, and this is my team here. So first, what is Muse? Muse is our multi-unit spectroscopic explorer, so a big IFU with 24 identical spectrograph. It's attached to the UT4 ISO 8-meter telescope on Paranal. It has a field of view of 1 arc-minute by 1 arc-minute. It has a spectral resolution of about 3000 and a spatial resolution of 0.2 arc-seconds per pixel. The important thing is it's operational since more than 3 years now. It is one of the most popular and productive ISO instruments. It has a very high efficiency, and it's a unique spectroimager, which means it delivers you from every single pixel in the field of view a spectrum, roughly 90,000 spectra in one shot. So this is how it works. A quick sketch here. So we have this field of view of 1 arc minute by 1 arc minute. It is sliced by the splitter here into 24 individual slices, and each of them is put into a dedicated spectrograph. So we have effectively 24 spectrographs here. Each of those images is then sliced in a second step and brought to a CCD. So this is one of the raw images which we have on the CCD, and we have 24 of these in one shot, 4K by 4K each. These are big files, roughly 1 gigabyte in size. They are kind of challenging in terms of data volume and data complexity as well. So we have to process these 24 extensions of a FITS file in order to have, in the end, the goal is to have this data cube, which has 300 by 300 spatial pixels and a spectrum for each of these pixels here. The Muse pipeline itself was delivered by the consortium, who also built the instrument. It is running on Paranal as a quick look pipeline used for science quality control. It's also run at the ESO headquarters in Garching, used for creating master calibrations and instrument quality control. And it's also available as a public pipeline. The science data reduction is done by the GTO teams, of course, so they have their guaranteed observing time. They are running their own data reduction chain, and they have their own data center. However, what are doing the other observers who are not directly linked to the GTO teams, they might have difficulties in processing these data, so ESO decided to process all science data and offer the data cubes through their archive to all users. The goal is obviously to override the data reduction barrier, so meaning that you can download these data and start with your scientific analysis right away. The science data processing requires a careful orchestration, so we have in total 5 recipes in 6 different steps. A typical data set consists of roughly 4 exposures and sometimes with an additional sky pointing. This is done on a multi-core machine, so naturally we would need 24 cores because the recipes are internally parallelized. Roughly 100 gigabyte of memory. It takes about 2 hours if we do it in one stream. So the end output would be 1 data cube from the original object pointing. And if there is a sky pointing, we also process the sky pointing as a standalone data cube, which might offer serendipitous science in addition to the original one. In order to derive or to maintain the best quality of the data, we work with pixel tables until the very last step, which means we do the rebinning only once and at the latest possible point in time. The products are flux calibrated and sky subtracted data cubes, which are science ready. Up to now, we have ingested up to 6,000 such data cubes. They cover the entire time from start of operations and include also data from science verification. These are data at the OB level. Observing block is a single observation, roughly 1 hour maximum for operational reasons. This is one example here. So this is a part of the Hubble Deep Field. So if you compare the HST image here to the Muse data cube, you see all the structures here. In addition to the image from HST, you here have a spectrum, and this demonstrates you the power and the discovery opportunities in these data. So here we see a scan through the data cube shows you what kind of information is in these data. So you have all the velocity curves, you can do chemical analysis with these data. So this is a very powerful thing. However, it was clear from the beginning this is not good enough. We have to go deep because we see that more than half of all Muse programs actually achieve or attempt to go deep, which means we have multiple visits of the same targets. And many of these do not occur in the same night, but of course are spread across a semester or a year. So we have to find all of these candidate observations and then select them and optimize them for a specific scientific case. Up to now, we have optimized them for really going deep in order to collect as many photons as possible, but there would be other options. They're not so trivial to find in service mode. For instance, the execution is always optimized for the prevailing conditions, so there might be cases where an OB is scheduled but then aborted, re-executed the next night, and so on. And then we select, and we start the processing. So we do, again, complete reprocessing starting from scratch at the OB level, and then in the last step, we combine all these products to the deep product. This is rather memory intensive because, again, we want to try to use pixel tables up to the latest step, and when the latest step, the merging and the rebinning of the information is done, we need to load all the input data into memory. So we see an example here. This is again a Hubble Frontier Field, a lensing cluster with emission line objects out to a redshift of 6.6. 15 of these OBs have been combined. They spread a total time range of 145 days. 58 input files, 11 hours exposure time at the VLT. There is the need to do individual calibration night by night in order to remove all the instrumental effects and all the atmospheric effects night by night. And then in the second step, do the deep combination. Something about the processing itself. So the memory which we need scales linearly with a number of input files. We have a machine which has 2 terabytes of memory available, and this means we have currently an upper limit of more than 120 input files, and this matches nicely the biggest data cube which we need to process so far. The effect of combining deep is visible here, so a single exposure gives you, if we use that close up here, roughly this kind of image. An OB, so 4 of these covering 1 hour, looks like this. And the final combination, 15 OBs, of course, increases dramatically the signal-to-noise ratio. We have processed so far more than 200 of these deep data cubes. And we are pretty complete until 2016, and we process further data typically after a semester is over, so we know there will be no more candidates and we can start the deep processing. Here we see, again, the power of the deep combination. So if you focus your attention on this area here, there is nothing to see, and then all of a sudden you see an emission line object, most likely a strongly redshifted galaxy, which is visible only in redshifted Lyman alpha at that point. And the same object here in the HST image is not visible at all. So you can discover objects here, and this is a huge bonanza in terms of data analysis. All these data products are available publicly from the ESO Phase 3 archive. Of course, proprietary rights are respected, so either the data are public immediately if the PI decided to waive the proprietary rights, or at the latest after a full year is over. Thank you very much.
Okay, okay.
Great stuff. Lennart, do you make them available through VO services as well?
There is connection from the phase 3 archive to VO services. Yeah. And we populate actually our data with header keys which are understood by VO-aware tools. Yeah.
Okay, yes, one more question. Yeah.
Yeah, thanks. Is it possible for groups who are doing their own data reduction to apply the same deep stacking techniques on their own systems with the pipeline you make available?
The pipeline is public, as I said, so you can download the pipeline and actually also the reflex workflow, which enables you to interact with the data products at intermediate steps. This is possible, yes.
Okay, thanks.
Okay, let's change our speaker again. Okay. Thank you very much. And now we are going to have the first lightning talk. Romain Thomas will present a 3-minute talk without questions on the Spartan project. I take LT1.
Okay. Okay. Hello, everybody. Thanks to the organization for this change of schedule of last minute. So I'm briefly going to talk about Spartan. So Spartan stands for Spectroscopic and Photometric Fitting Tool for Astronomical Analysis. So it was born because now we are entering a time where we observe objects, but we also reobserve them with different instruments at different observatories. So for big samples of objects, we have photometry, we have spectroscopy, sometimes we also have multi-spectroscopy. So we built Spartan to tackle this problem, and so Spartan is a multi-component galaxy template fitting, and it aims at using all the available data, so photometry and spectroscopy, to increase the constraints on the physical parameters of galaxies. So for the design of the tool, we instead of doing it ourselves, we ask a sample of extragalactic astronomers to know what they want to have in this kind of code. And so we propose them a market study-like survey. And the answer of this market study designed the code itself. So we didn't have to think about what putting in there. So we are spanning from the user interface to the data formats to the ingredient on the models. And the tool is, and Spartan is composed of 3 main parts. So you have Spartan Fit. So it's the main part of Spartan. So this is the fitting engine. So here you have examples of fitting of the same object with different combination of data. So from the multi-wavelength photometry to multi-wavelength photometry and multi-instrument spectroscopy. Of course, when you have a given combination of data, you want to know what constraint you can expect from this combination. So we created Spartan Sim, which allows you to create mock galaxies of your given combinations. And then the last part is a Spartan user interface. So there is 2 user interfaces. There is a text-based, so in the terminal, which allows you to configure the code. And there is a graphical user interface for the visualization of results. So the Spartan will be likely public released early next year. And if you want more information, there is a poster number 30 if you want to come. Thank you.
So before breaking the session, So just short announcements. Then, okay, as we said before, send your PDF files for the posters to poster@edas.cl. The paper posters will have to be removed by 1:30, and Nuria is going to make a short announcement.
Still on the subject of posters, during this next break, can you please, please, please vote for your favorite poster? Write the poster number on a piece of paper, put it in the fishbowl, which I will put back at the registration desk. You have an hour left. This is your chance to give somebody an extra 2 pages in the proceedings. Thank you.
Thank you, Ron. So, Duto, and this concludes the session on observatory operation software.
and she will be talking to us about One Pipeline to Rule Them All, version 2.0.
Okay, good morning, everybody. As some of you might know, I've been reporting on Gemini's effort to create a pipeline for a few years here at ADAS. We did get something, but to put it in context with a talk we had this morning, let's say it was working, but we certainly didn't have the quality attributes. So last year, we actually had an opportunity to rewrite the infrastructure from scratch. So we already had quite a lot of data reduction algorithms. So those were refactored to work with the new infrastructure. But the infrastructure itself was basically scrapped and rewritten from scratch. We did it in 8 months, most fun we've had. So just to explain what we do at Gemini, we have lots of facility instruments. So we do optical, near-infrared, imaging, spectroscopy, all flavors of spectroscopy. And currently we have 7 instruments with 2 new ones on the way. And creating a brand new pipeline every time for every mode, every instrument, it's simply not feasible with the amount of effort we have. So we decided to write one infrastructure and try to make our data reduction algorithms as generic as possible to maximize reuse. So I want to present quickly the various main components of the pipeline. It's going to be a really broad overview. And after that, I want to spend some time exploring some of the lessons learned, because clearly there was some lesson learned if you get to the point where you need to rewrite from scratch. So the first component is astrodata. This is our data abstraction. At Gemini, we use FITs, MEFs in particular. And of course, you all know headers, for example. Just let's take the classic case of headers. Each instrument have their own headers. There's some fit standards, but really the name, as long as it's 8 characters long, can be anything. So we wanted a uniform interface, for example, to the headers. And here at the bottom, I have some examples. If I want the gain in my data reduction algorithm, regardless of the instrument, I just want to ask for the gain and get a value. Same for the filters. Sometimes you have 3 filter wheels. When I concentrate on data reduction, I don't want to know about the details of the headers. I just want to know what the filter is. So that's one aspect that astrodata provide. Internally, it is stored as ND data. So that's a switch we've made in this rewrite. So while we're using FITs, the FITs is just a layer that does the read and write. Internally, we work with ND data. And all the instrument configurations are in a separate module, so astrodata itself is not limited to Gemini or to an instrument. And in fact, just this week, Ken Anderson and I hacked a few things with the SOAR team, and we got some SOAR data to work with astrodata. Then we have the automation infrastructure. We call it the recipe system. And this is what actually takes an astrodata object, look at our library of recipes and primitives, and match them together. So here's an astrodata object. Let me see which recipe is the most appropriate primitive sets, bring them together, run. It also has the ability to look at either a local, on the user computer, local database, or a Gemini, our main database, for process calibrations, and it goes and finds the most appropriate one. So it can be very, very hands-off. And in fact, at night, it runs in the quality assessment mode, and it just runs. The observer doesn't need to do anything. There's both a programmatic and a command line interface. And as you can see here, the command line interface, reduce name of my image or my set of images, and it just goes. Of course, we want to use the same pipeline for our user science quality software. So we do want to allow them to build their own recipes if they want. Here's what a recipe looks like. One driving principle for the recipes is we want this to be readable to a scientist that might not know anything about Python. So as you can see, even though this is a Python function, there's no logic, no nothing in there. It's just a list of the steps in a scientifically meaningful language. Each of these steps are the primitives. This P for the software people, it's basically a class that has all the primitives that are applicable to this data in there. So you just call them there, data gets moved through this, this object. And the primitives can be inherited, so that allow us to really optimize the reuse of our algorithms. So in this specific example, some Gemini level primitives, GMOS images, and then we also have some that are completely instrument agnostic that can just be mixed in as needed. Now, lesson learned, or a bit of humility here. And what I'm going to present, you're all going to go, oh, well, of course. Yes. So we had to, the first version, we were plagued with the same problems you've all had, limited effort, time constraint, other projects kicking in, but we needed to get something going. So some decisions were made that were not optimal, but hey, we got a chance to fix them. So when we thought about Astrodata, we wanted it to be useful to other people outside of Gemini, except that we built it really based on fits. Well, there's some other formats out there. So this time around, we fixed that. Internally, it's ND data instead of being more or less a big pie fit. And we actually gain a lot out of it because now we have error in data quality plane with the arithmetic. It's just we get it for free. We had our own in the past, but that meant we had to maintain it, and it was also not as slick as the one offered in ND data. The fits layer that we need is really just an add-on. So if you have the new JWST format, you can just add your add-on, your layer, and you're good to go. The other one, in our case, we chose Python, but we forgot to embrace Python. So we had a lot of mini-language, custom parser. We had something really ugly. Some files and directory had to be named a very specific way. So my advice, just don't. It might, at the very moment, might seem like the very simple, quick hack that you can do, but you're going to pay for it tenfold. So just don't. The other one that it might be a bit more forgivable, as mentioned, we had a requirement, we wanted the recipes to be readable to any scientist without knowledge of Python. So at first, we wanted the recipes to be just text file. The problem is if you have a text file, then you need to write the parser for it. And that became really ugly, really fast. We couldn't even pass Python types. It just got really, really messy. And we still wanted this requirement, but then the key was, well, let's sit down and think a bit. And sure enough, there's a very elegant Python solution. This is just a Python function. It's still just as readable. So if you stop, think about your problem, you can find solutions that are elegant. And as I mentioned before, the quick hack, you'll pay for it. The other one, this is a boring slide, but I said, do not abuse abstraction. In this example, I tried to get a nice graphic slide for this one, but so Ken gave me this example as awful abstraction. It's a class that needs another class that needs another class. It was several levels deep. And at one point I said, well, could you graph this for me so it would make the slide a bit more interesting? He just laughed at me and said, no, I tried. I never could figure it out. So it was a real mess. And when he did the fix, because Ken took care of the recipe system, he was able to replace this awful thing with just a function call. There was no need for the complexity. So I'm not saying don't use abstractions. Sometimes they're useful, but just keep it down a bit. So the result is that overall our code base was reduced by half. So that is massive, massive improvement. Because especially with the small team we have, the less code we have to support, the best. So, and it was not just in the infrastructure. The changes we made in the infrastructure meant that our data reduction algorithm that we had to refactor also became much shorter because the system was a lot more friendly. Like the switch to ND data in particular made a big difference. And of course, code base is cleaner, it's more Pythonic. We can actually grow the system now. In the old system, adding a new mode, we never really knew exactly what would happen. This time, we did it in a few days for the SOAR people, just hacking here in the hallway. And my final slide, a final word of wisdom, is when you draw your multiple level of abstractions and it starts to look like modern art, you've gone too far. And a message for the managers among you, sometimes it is better to rewrite everything from scratch instead of trying to fix what is literally unfixable. So listen to your developer. I'm not saying always agree with them, but consider it seriously. And if you've chosen Python, you probably had a very good reason for choosing Python. So let Python be Python. Thank you.
Hello, thank you, very nice talk and great idea. I'm curious, so a telescope like Gemini is going to continue getting instruments on timescales of years to decades. Do you have how do you envision this growing over 10 or 20 year time frame?
Well, currently we have 2 instruments on the way. The most advanced one is Ghost. And currently, we are not developing the data reduction software for Ghost. They are developing the data reduction software with this infrastructure. So we actually work with them. And in fact, what happened in the case of Ghost, when they started, they were using the old system. So we arranged with them in August, they delivered a milestone. We took the software for 2 months, refactored their software to the new infrastructure, and give it back to them, and now they're running with this. And it's going to be the same thing for the next one.
Another question?
Yep, just here.
From my experience of dealing with pipelines from ESO, which have kind of similar infrastructure in the concept, I mean, when it's a recipe. Mm-hmm. If something is missing in the algorithm, for instance, or the algorithm is oversimplified for a certain part, it's getting quite hard to add a block into it if you're an external user. Mm-hmm. So like my student had to find a way how to stop a pipeline midway, pipeline for UVis, do some post-processing of intermediate results, and then feed it back to the pipeline. How do you envisage this in the case of Gemini?
Just to put something in context, I'm an astronomer myself. I don't believe in pipelines, yet I work on one. So that exact problem that you've described is something that I'm very likely to want to do. So at this point, I don't see any roadblock in the system we have in order to allow this thing, but I can guarantee you I'll make sure it's in there, this possibility.
A final question? Oh.
So the way that you specify the pipeline is just with the series of primitives. They specify no inputs and no outputs. So you can't visually see what the logical flow of data through those steps is. Can you explain how the primitives define what their inputs and outputs are and how you kind of validate that the wiring diagram gets everything to the right place?
I didn't present it, but there are some input and output parameters. It's just that in your recipe, if there's nothing presented, it will just use the defaults. Our next step, currently we've been using it for quality assessment at the telescope, so we just use the defaults. But for the science quality version, and this is something we need to attack in the coming months, is we need to provide a really nice interface to the input parameters so the science user can either on the command line or in a configuration file of some sort, or even by editing recipes themselves, they can set the input parameters to do the little tweaking that is often necessary for science optimization. Does that answer your question? No. Well, I can show you some code later. It's quite.
A poster or a paper on the system?
Not specifically on your question, but if you grab me, I'll be happy to show you what it looks like. It's a Python function with parameters and defaults, and we have a parameter file that currently is being imported by the primitive, and the parameter has a dictionary of the various allowed input and defaults. Good? Okay.
Right, let's thank Kathleen again for a very interesting talk. Our next speaker will be Daniel De Vost from CFHT, and he will be discussing with us the optimization of the nighttime at the Canada-France-Hawaii telescope.
All right, push that, yeah, perfect. Okay, thank you. So first I'd like to thank the organizers for giving me the opportunity to talk to you about work we do at CFHT. It's my first time in Chile too, so that's giving me the opportunity to see Chile. I have to admit right off the bat that I am one of the lazy ignorants. So this is not my work. This is the work of others, mostly the software group. Among others, Billy Mahoney here, who's here in the audience. Kenoa Whittington also is here. And I haven't seen Matt Wilson yet. Oh, there he is. We didn't lose it last night, which is good. So I'll talk to you about SNR QSO at CFHT. So how we optimize the nighttime. But first, I'll just talk to you about CFHT so you know who we are. So we're 3.6 meter at the summit of Mauna Kea. We have 4 instruments that we operate in Q mode. So 2 prime focus imagers, WIRCam and MegaCam, and 2 Casgrain focus spectrograph and spectrograph imager, Espadon and STEL. And all these instruments are operated in Q mode. So that means that we haven't had a classical run, I think, since 2012. So we're operating in Q mode 100% of the time. And these are the benefits of the QSO. So to me, it's a first optimization that we did of using the nighttime at CFHT. So this graph shows in red the amount of time, that we had in QSO. And here, starting here, it flattens because we use it 100% of the time. And these bars here are the number of papers, basically. So there's some kind of a correlation there. And it's quite impressive how the QSO system has helped CFHT. So other than that, we have a whole program where we try to do better use of the nighttime. So in the last few years, several efforts were started toward this goal. So first, we vented the dome to minimize turbulence. I'll talk to you a little bit about that. we minimized the readout time on MegaCam, and we cut Espadon readout time by a factor of 2. And we implemented the SNR mode into our QSO system. So I will talk to you about these two things, really briefly about the dome vents, and then more about the SNR QSO system. So here's the dome venting project. So we literally poked holes in the dome, and here are the results, basically. So that's a 2 years before, 2 years after type of graph. So before is red, after is blue, and this is image quality here in arc seconds versus the number count. And you can see here the 0.5 arc second bin has doubled since we opened the dome. So that really works. I mean, and it gave us better seeing. So what do we do with that seeing, right? If you don't do anything, you'll just observe your programs deeper. The programs that are accepted, you'll observe them in better seeing condition. So we decided to move toward SNR observation. So this is something that was presented here at ADAS 2013, not here, but in Hawaii. And that was presented by Jean-Charles Cuyan. That was really the concept that was presented. And here I am in 2017 presenting to you real results. Right now, the system is implemented, it works, and I'll show you in the end what we gain. We gain quite a bit. So instead of observing to a certain allocated time, we observe to a certain allocated SNR, right? Those of you who have observed, we've all done that. You check your depth and you try to integrate to that, but in a QSO system, it's really hard to do that. And you'll see the changes we've made. So we've implemented it first on MegaCam. So this is what Jean-Charles presented at ADAS 2013. And this is basically a aperture photometry model. The background, full width f-max, these are your main sources of noise. Background is quite important, actually. So here's the system for MegaCam. So that's phase 2 input, executing the observations here, that's all done. This is done by the user, this is done by the observer. In a regular system, you just do that here. You execute, and then you keep going, and your phase 2 users get you data. Here what we've done, we've integrated that model, and we use Elixir, the MegaCam pipeline, and also SkyProbe, and all sorts of device to estimate the weather conditions. And then using that model, we recalculate the exposure, and then we execute, and we keep going. So it's fairly complicated. It's, you rely a lot on your model. And that's some kind of a problem, but I'll talk to you about that later. Here's the gains, basically. So in red, so in the y-axis here, you have actual over requested. And in red, it's the SNR, and in blue, it's the exposure time. So ideally, we have the SNR here, the red bar should be all at once, so we're not doing too bad. So we're targeting the SNR of the program. But here, look at the blue. I mean, the blue, since we're constantly below 1, we're getting to the SNR that the PI wants in a shorter time. So basically, this is saving us time. And some programs like that, I mean, we overshoot, and we haven't even exposed half the time. So the seeing on Mauna Kea plus our dome vents help a lot for that. Here's a plot that was given to me by Stephen Gwynn. This is one of our big programs, large programs, R-band observations and U-band observations. And this program uses the SNR mode for the R-band. So you can see how much better, this is depth. So you can see how much better grouped in depth the images of the R-band are compared to the U-band, which does not use the SNR for some technical reason. So you gain also there. Your observations are much more uniform. And this program that we're using, it's called CFIS. It's a program conjoined with Euclid. And uniformity is really important because they image a huge chunk of the sky. So you gain that also. On top of the time, you gain uniformity in your data. Okay, so then seeing the results we had with MegaCam, because it wasn't clear at all that we were going to gain, we decided to do it with Espadon, which is a high-resolution spectrograph. So the concept is quite different, honestly. So what we have the leisure on Espadon of having an exposure meter. So it's a photon counting device, basically. So what we did here in red, what you have is the counts on the exposure. Here in green, that's your SNR target. And in blue is a model that we developed to relate the number of counts to the final SNR of the reduced data. So this is final SNR that we get. So we give that to our ROs, and when they reach the SNR, they stop the exposure. It's a completely different concept than what is done with MegaCam. So this is MegaCam. So using an exposure time calculator, we get rid of that. All the pipeline stuff to reduce the data and estimate the SNR, we don't need it. We get rid of that too. There's no need of using the ATC or the model of aperture photometry or whatever model to to estimate the SNR. So the big changes are here. So what we did basically, what we did is feed the exposure meter, like I was explaining earlier, and stop the SNR exposure when it's done, and then we keep going like that. And sometimes it's not SNR. So it simplifies tremendously the operations when you have a photon counting device on your instrument. Not all instruments can do that, of course. It's harder with an imager than with a spectrograph. So here's the same graph that I showed earlier, but for Espadon. So same thing, actual versus requested for Espadon, SNR, and actual exposure. Some of them were below, but we're mostly there to 1. This one here, we overshot quite a bit. And again, you see that the blue is way lower. That's what you want. So overall, using all of that, we've been using it since officially since the start of 2017-A. So that means that the programs since that time have to justify getting out of SNR. So it's the default mode. So of course, you cannot do SNR on all the science programs. Some of them, it's just not, you cannot do it. So these guys have to justify opting out, and they do opt out. But those that we can do it, and there's way more with Espadon than MegaCam, we have a little bit of a hard time convincing our MegaCam users that this is the right way to go, but it's coming. It's better than it used to be. So with that, the time saved, requested minus actual, since 17A until, well, when I gathered that data a week ago, we saved 58 hours on MegaCam. So what I mean here by time saving is requested minus actual. So requested comes from our phase 2 database. The user puts that there. I want that SNR, and they put an exposure time there. So if we subtract what they put in phase 2 minus what the time we use to actually get to the SNR, we count 58 hours with MegaCam and 43 hours with Espadon. It's an enormous time saving. And for us, well, it's a very good justification for having the vents and being on Mauna and trying to squeeze more programs into into less time. So, en conclusion, that's my last slide. So observing the SNR mode allows us to get more programs completed in a shorter time. Estimating the flux, if you can use an exposure meter, use it. It's infinitely more simple, and it's way more efficient. And so I think with Espadon, we've proven that sites like Mauna Kea are beneficial to imagers, of course, but also to spectrographs. Because we do shorten the exposure time quite a bit on our spectrograph. It's a fiber-fed spectrograph. So a smaller PSF will give you the flux you need in a shorter time. I'll stop here.
Daniel?
Nice talk. Thanks.
Thank you.
Thanks for that. I have a question about the performance gains that you showed there, the hours saved, and I'm wondering whether or not, always thinking about a bias, is it possible that the ETCs that are being used by the astronomers are weak, or is there something really intrinsically better about what is happening here? Because you would expect the ETCs to do a better job.
To pick this up, yes. So if you pick the right seeing, the ETC is usually pretty good, but all this saving is mostly due to the fact that we have better seeing than expected and lower background than expected. So if you feed the right parameters to the ETC, it should give you more or less what you're going to get. So our PIs give us an estimate of what they want, mostly upper limits or where we want to be around, and we try to target that. But if it's lower, then we start saving time compared to what they've put into the ETC.
Yeah, so this is basically running an ETC with the observed conditions, which is fine if you know what you're looking at, which is why you do better. So you say you know the sky brightness, you know the seeing, you can run the ETC and you get a signal to noise estimate. We're going to be doing the same thing on PFS, the prime focus spectrograph we're putting on Subaru. But it's straightforward if you know what you're looking at. For a fiber spectrograph, where you've done targeting, there are other errors. So if you know you're on a galaxy of the sort you thought it was, fine. You can figure out the signal to noise when you've got enough signal. The problems come when you say, what if I targeted it wrong? Maybe I'm expecting to see oxygen lines and I'm not seeing them, in which case that doesn't help you. But you can get the other type 1, type 2 errors potentially, when you can say, I couldn't have got that much signal just by a crude measurement on the outputs, if I really had the target I thought I was. So there are some extra games I think you have to play when you're folding in, have I got the right target, as well as what the conditions are.
That's correct.
And those are real gains as well.
Yeah, it's very true. Yeah, and with Espadon, we kind of ran into that because with Espadon, it's easier than it'll be with you guys with PFS because we're only looking at stars. But we ran into that at the beginning when we were using a different spectral type than what the PI had requested or what we thought we were looking at, and it does affect your time, so you need to be aware of that.
Right, I'm afraid that's all we have time for, so let's thank Danielle again. Our next speaker will be Ignacio Toledo from ALMA. Ignacio will be talking to us about scheduling solutions in the era of big observatories, giving us the ALMA experience.
Okay, it's ready. Okay, thanks. Minutes, all that I have. I hope that I can cover all the things that I want to cover in this talk. So let's go to the problem right away. The thing is to present actually this shielding algorithm. I changed something there, development in the area of big observatories, and I want to talk about the ALMA experience. And it's actually more about experience than technical stuff, what I'm going to talk right now, in the hope that this works for other people. So we have the first slide, and in the background you see what you would expect at an astronomical site at all times. And optically, it can be what you expect. In radio astronomy, you can also get things you can observe during the daytime, so maybe you won't see the stars, but it still is a nice picture. But then we have this moment of reality that we never want, but they happened. So the shielder has to answer some particular question. I'm here talking about scheduling in the sense of the particular problem that is need to be solved to answer this question, which is what is the best thing to do under current conditions? And this is what it was mentioned, or it was a summary of the scheduling subsystem design document in 2009. So this is what the scheduling that I'm going to talk about here, it wants to solve. I'm not going to touch how it connects with control or put things in queue or other stuff. It's this part, this core of the algorithm. So the first thing is to define what is the best thing, the best. And you have a lot of measurements or a lot of metrics that could help you to determine what is the best thing to do. Is it short time best, what you can do in the short time? It's a long time best, in the sense that you have to, for example, finish the higher amount of high scientific ranked projects, but at the same time, you have to be fair with the executives, with the stakeholders of ALMA, and give their share of time of ALMA to each of them. You could have as the only goal the scientific best, so the priority should be always based on the ranking, or is the best for the whole observatory. Because at the observatory, you also have astronomers that would like to test a lot of new things because it's very exciting what you have at the observatory. So you have different things. And for ALMA, as it was defined in that document, is to do the best possible science. And in software terms, that translated into executing the scientific most important scheduling units that has the best chance of success under the current conditions. And then you have a whole document defining how to achieve that. So, the second thing was defining the current conditions, and this is something quick that I want to talk. The whole observatory knew that one thing that was going to be affecting current conditions was the weather, which are not under ALMA's control, but we already know that we wanted to take advantage of the periods where we had a little amount of water vapor in the atmosphere. That's one of the main reasons why ALMA is at 5,000 meters. And we should be, and also the periods of stable atmosphere, and should be used always for the higher bands, those particular periods. That's one thing. And then the other thing that you have to take into consideration, and it was mentioned in the document, is that the resources are given. And I said, in contrast to other kinds of scheduling problems, we cannot easily state the goals of scheduling in such terms as optimizing resources and conserving time. So what does it mean in the practice? That the array configuration, where the antennas are going to be, or what are we going, or the calendar that we're going to have in a year is something given. The scheduler was not going to solve that in the beginning. It was going to try to optimize over that in the short-term periods, trying to do the best science. And then we have a long period of time when, starting for that summary, the design, research, and development was done. And this started in 1999 with the first document from Wright, where the discussion kind of opens officially about the scheduling for ALMA. It keeps going with the design philosophy. You start to see that we are talking about dynamical scheduling because we know that the conditions change a lot, but it's also, I start to say it cannot be completely manual. It needs to be at least interactive because there is a potential for optimizing this observatory, and we need to optimize it because it's a big observatory. Then we have more stuff that is being found out in the development and research and design period. ALMA Memo 47, they start to talk about the stringency, given that we are not sure about the weather conditions or what are going to affect our weather conditions. We are talking about taking into account that most probably we're going to have to deal with probabilities to plan in the long term. Then there was this presentation of the dynamical scheduling in ADAS 13, 2003, already 14 years ago, where they gave this first ideas on how it should be implemented. And then you have a lot of people doing research in universities, and you have Gregorio, Hofstad, Mora, Garcés, Avarias. Some of the people actually works in ALMA now. Some of the people actually developed the subsystem in those years. You have an ALMA operations plan, things were keep going. Finally, you have the shielding subsystem design document in 2009, and we come to cycle 0 and the deployment in production and the start of early science. So that's a picture in the happy years of 2011. We had the still antennas doing science, it was working. Finally, we have ALMA online, and we were getting great data from the sky. It was working really well. You will see, if you see the slides later, you will see that there is small annotations down there. And this is something that was really clear. All of these sites come from the works from Terry Pratchett and the DIS work. And sometimes they are kind of very applicable. And this is particularly true. Something wonderful is what's going to start at that moment if you take the long-term view. But in the short term, something terrible was going to happen, okay? Because we enter operations. So the operation starts, and this is a period where life, at least for me, was simpler. I was just starting in 2011. I missed all the development process, okay? At that point, I didn't know what all the design was before. I was completely new to this subject. I studied astronomy, entered as a data analyst. People still didn't know in the observatory what were we going to do. But something that I noticed in the control room is that the cellular panel that we have to build the queues were to pick a XB that was already selected by some astronomer using an Excel spreadsheet. Okay, so that's how it was working. And at some point, and I was completely naive at that time, somebody, my boss at that time, approached me and said, Ignacio, you seem to know Python. Do you think that you could create this script to produce a quick list of SVs which are over 20 degrees of elevation? And this is when life started to get much more complicated. By the way, that's a quick note. I would have liked to show the work at the time, but this is an advice for people that believe that Google can store all your work forever. Google deleted my account in 2015. I'm still mad about it. Sadly, I still need to use Google products. They send me an excuse at the end, but I never recovered all that data from those years. It was terrible. It's sad. Artificial intelligence. It works nice, but sometimes it can kill you. But some evidence was found. Last night I was talking to you with John Hibbard, and this is one of the Excel spreadsheet that John Hibbard created to work at the observatory. It's a spreadsheet where you have all the projects for cycle 0, and this was giving you information about what time things were going to happen. I'm going to try to be quick a little. Let's analyze then what actually happened, because we cannot just say this was a problem that people was doing the wrong job or was doing, or nobody did the job that they were asked to do. No, it was not like that. No. So the experience taught what it was happening is that I think we had a lot of plans for operations that came from a previous observatory experience that were not applicable to ALMA. Okay, I think this is my personal opinion. After that kind of question, that was a review at the moment of how we were doing with starting an operation. Is ALMA operating as expected? It's no, but not because it was a bad planning, but it was because we have a different expectative. And one of I want to show, so there's two reasons. The first, as I mentioned, there is operational change, and I wanted to show quickly some examples. At some point when the development was being done, everybody thought that we were going to have a standard or a static arrays that will change in a planet calendar through the year, so the scheduler needed only to have somebody to tell it what is the configuration right now. But then in the reality, things were much more difficult. ALMA moves the antennas in different paths. Not all paths are being used. Sometimes some paths are not available, so you have to move the engineer has to move the antennas to a different path. So the arrays are not necessarily exactly as planned. And also the problem was that you have a long period of time in moving the antennas between configurations, and you cannot afford to lose the observations for 2 weeks or 3 weeks waiting for the antennas to be moved. So you need to take care about that issue, what to do in those moments. The weather, I think, is simple and predictable, and is what's much better than we expected, maybe. it's just to put an example. I don't want to go to the details now. And also the planning was more complicated than expected, okay? Because you can offer something to the community, but the community can ask for a different thing. And when you start planning, for example, this is using the A and B grade projects and how much pressure they were putting in different LST ranges for different configurations in cycle 4. And you can see that there are some particular configurations that are completely oversubscribed, while others don't have enough projects to fill up. And that's a huge problem for the planning. But this is the main reason I think that we had a problem when starting the operation, was that if we forgot to earn the trust of the users and astronomers. There is a lot of point of why they should trust the machine. Why we had a spreadsheet, an Excel spreadsheet, and this I was talking to John Hibbert. We had a panel that was showing you a smallest list of the SBs that you could execute. But that panel didn't tell you why they were being picked. And astronomers were really upset about that. Why should I trust that? They couldn't even play to what we are going to have in the future to observe or not. So, and the funny thing is that in 1999, it was mentioned that to make the best use of ALMA, a dynamical scheduling program should be able to adjust observing parameters according to the weather, and it must do it so in a way that leaves the human observers feeling in control of observations. A final, can I? Yep. So the information must be transparent. This is something that we learn. These are the questions of the astronomers at the end, but how we are reacting to the lesson learned, and this is something that I would like to point out. We don't talk too much about this in ALMA, and maybe it's because of this, because the winners, or when things are working, never talk about glorious victories. It's because they are the ones who see what the battlefield looks like afterward. And there's a lot of people down in the field, I think, and a lot of things that didn't work as expected. But there are things that are being done. And I think that we have finally seen that those that we need to take into account for the selection some clear criteria, and these criteria have to be aligned with what the imaging and quality assurance team is requesting, and they are learning also how to have a quick assessment on the quality. The astronomers need to be involved in the development of the schedulers somehow, and this thing, something that was good is that we implemented the whole algorithm in a Python environment so that it can be used by the astronomers. It hasn't been used so much, but this is something that we want to push. And finally, something that it was yesterday done is the Birds of a Feather session that we have, and that we are contacting people from the academia that is working on operational research. And that's something that is really helping. Thank you. Yes, to have a...
One quick question.
What comes next? What can you do with this?
What comes next in terms of optimizing?
Yeah.
There's two things. One, we were talking about this yesterday. One thing is to actually provide this Python library to the schedulers and to the executives and the stakeholders so they can actually see what is going on. And that helps a lot. Not only because they trust more the system, but they also find the bugs or the problems in your assumptions or your code. And that helps a lot. And then it comes the optimizing. And in this, reaching out to the experts from universities, I think it's going to be something really nice because there's a lot of experience there that we have not taken into account. And we hope that that's going to help very much. We are experts in the domain of the problem and defining the problem of ALMA. We have experts in the software implementing the algorithms, but we're missing experts on the optimization problem itself. And this is something that is important.
Okay, let's thank Ignacio again. So next we move on to the lightning talks. If you look in your program, we've already had the first one. So we have 4 talks. I believe there are 2 people still missing. If you're giving a lightning talk, can you come to the front row, please? And I'll remind the speakers that you have 2 minutes to speak and no questions. So for our first lightning talk is Igor Chilingarian, who's going to talk about P85.
Hello, everybody. So I'm going to present quickly my recent development on the data reduction for cross-dispersed shell spectra. I'm concentrating on intermediate resolution optical spectrographs, not the one that I used for exoplanetary studies, but mostly those that I used for fainter objects that provide spectral resolution from 4 to 10,000 and cover the entire optical domain in like 20 to 30 shell orders. Those instruments have much better throughput than normal shell, but they also have slits, and the data is a real mess. It's a nightmare, and you're really very hard to reduce. I often deal in my science programs with two instruments, FIRE and MAGE, which are both available at the Magellan Body Telescope at Las Campanas here in Chile. But analogs exist on many large telescopes at VLT, keck, and so on. The pipelines exist for them, but they're based on legacy packages, and this is the worst example of what I would call multi-layered coding. Don't mix with multi-layer coating of the optics. So it's when you have one layer of code, above it you have another layer of code written by some other people, above it you have another layer of code written by some other people. At the end it's unmaintainable, and it's getting less and less efficient over time. So we decided to build new pipelines and write them from scratch with minimal dependencies and reduce the execution time to the level that we can use them at the telescope. And we succeeded for both MAGE and FIRE, and now in a few minutes you can reduce an shell spectrum obtained at Magellan, and this has been tested already with MAGE in August. And we get very nice results on wavelength calibration precision, on flux calibration up to a few %, and correct for telluric absorption. So if you want to learn more, talk to me or contact me by email. Thanks.
Good afternoon, everyone. I am presenting the talk on next generation monitoring and control system for GMRT, an exploratory prototype for the SCA telescope manager. I am from Giant Meteor Radio Telescope from India, which is run by National Center for Radio Astrophysics. And this telescope is operational since last 15 years. At present, 33rd observing cycle is going on. Along with the major upgradation like a continuous bandwidth of 400 megahertz correlator, and 150 to 1500 megahertz continuous bandwidth. This telescope is having 30 dishes, each of 45 diameter, spread over 25 kilometer area. And along with this major upgradation, we are upgrading also MNC system. MNC system means monitor and control system. NCRA is leading also telescope manager package of SCA, which is consortium of 11 countries. NCRF is at presently upgrading the MNC system with keeping in mind goal of having open source control system framework evaluation for the SCA like a Tango. And new control system is aligned with the SCA control system like architecture evaluation, technology choices, and many testing elements. Along with this, therefore we have adopted the Tango. Tango is a telescope accelerator control objects which uses a Corba and 0MQ based middleware. We are supporting 5 subarray for concurrent observation and 1 engineering array for maintenance. Also, we are having 450 Tango device servers and 20,000 attributes. We support context-based user interface for the like astronomer, operator, engineers, which can access their user interface. Also, this support Python scripting interface, alarm, and exception handling, as well as end-to-end radio telescope chain. This Tango software has been developed in a such way that it can be implemented for any generic telescope. We have Tango expertise since last 4 to 5 years. This telescope can be used for learning and experiences for the SCA. Thank you.
Our next lightning talk is by Kim Dupree, and she will be presenting poster 127.
Okay, so once this comes up, you'll see that I was trying to go for the most simplistic slide possible. I think I win. Okay, so my poster is poster 127. You probably are not going to be able to see it before it's taken down, but I also have my email address up there, so if you like what you see, please send me an email, or if you can find me during the conference, come talk to me, because I love to talk about my work. Basically what this is about is designing a notification service for HST and JWST. The top box is a very simple design. We have a user can subscribe to a program and get automatic notifications for when new data is available, when data becomes public, or when data is reprocessed. I'm not going to talk about that. On the left-hand side, you have the notification service, which is in two pieces. The middle piece figures out when we have data, who do we send it to? I'm not talking about that either. I'm talking about the thing that's way over on the left, which is determining what data actually is good enough. I shouldn't say good enough. What data we should send notifications for. So at the bottom box is the general flow. This is using the actor model. I implemented it using the Akka toolkit. I don't have time to talk about any of that, so if you're interested, talk to me or send me an email. So basically, we have a controller actor, which handles all of the flow for the entire project. So when we get new data, we put a row in the database saying, we have data. A poller runs, querying the database, checking that table. If it finds something, it says, hey, I found data, and the controller sends it to the CAOM actor. So we can't actually send out notifications until the data is in CAOM. So the CAOM actor says, hey, is it in CAOM? It finds the answer, goes back to the controller. If it's not in CAOM, it actually sends a message to the database saying, it's not in CAOM yet, try again later. Update the database to say that. If it is, it builds a message, and then it sends the message, which goes to the middle box at the top, which then figures out who it should get sent to. That's it in a nutshell. Thank you.
Last lightning talk and our last talk for the conference is Bruno Sanchez, who will present poster 118.
Thanks. So what I'm going to present is something that we came up when we were trying to design pipelines for processing images of telescopes in remote places where we have low connectivity. We try to perform an electromagnetic counterpart search for gravitational waves, and we have several small telescopes, so we needed quite simple pipelines, and we needed to do many of them, so we figured out how to perform this using MVC model, which is a pattern for this MVC model view controller for designing several programs. So we built it on top of SQL Alchemy so it can work with a database. It's a full Python implementation, has no other dependencies. It can also build quality reports and auto documentation based on unit testing. We have a quality assurance index of your pipeline so you can trust it without going to the place and check the data. We have, for example, if your tests are failing, you have a 0. But you also have metrics including the code coverage, the ratio of your functions being tested, and we also have a style errors metrics. We also have capabilities for data parallelism using branching in the pipelines, and the overlay of a pipeline should look like this, where you have one central database and several processing steps are interacting with data, and alerts are notification to the user results. So we find it useful for many tasks. We have it completely open source at this direction in GitHub, and we encourage you to write emails to us and issues in the site. We also, you can go to check our astronomy and computing paper. I think that's all. Thanks.
Thank you very much. And shall we thank all the speakers in this session, please? There we go. That's all right. All right, so we come to the end. Thank you. A few words before we go for lunch. I hope you've all had an excellent conference. I hope you've had fantastic discussions and learned new technologies. I hope there is one thing, one application, one technique that each of you can take back to your institute to try out, whether it's Jupyter Notebooks or Drupal or looking into machine learning techniques, or improve your understanding of statistics, or fight to keep your software simulators in your software plan. I hope it has been a useful week. I know it has been for me. If you've not had the time to read all the posters, and I have to put my hand up and say I haven't, they will be uploaded to the website. The flip side of that, if you're a poster author, please, 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 please send the PDF of your poster to poster@adas.cl so that we can put it on the website and so people can read about your work. Similarly, the presentation slides will be on the website. A couple of people have asked me about the timescales for that. I'm not sure. I'm going to defer that question to Jorge. So allow me to remind you that you have until the 30th of November to finish your manuscript, revise your manuscript, and upload the final version to the website. On Monday, I mentioned to you that this was going to be a large conference. And now that I've been given the final numbers, I can tell you that in terms of attendance, we've had almost 400 people here. And in terms of number of posters, it's huge. So it's a record-breaking conference as far as ADAS is concerned. So well done to all of you. In terms of media, the LOC have been working extremely hard throughout the year, in fact. We've had 90 press releases. In social media, the Facebook Live has had more than 4,000 views. So attendance to this conference is not just all of you here, but we've had participation from around the world. An interesting statistics, the Facebook Live post that in English that has had the most views was Michel Perron on diversity. That had over 600 views. And in Spanish, it was Mauricio Solar, who talked about the Chilean VO, and that also had more than 600 views. So we're having really good participation. So some thanks. I would like to thank our ADAS 27 hosts, ISO, ALMA, and Universidad Técnica Federico Santa Maria. This conference would not have happened without them. So let's give them a round of applause. Of course, our government and industry collaborative sponsors, our commercial partners, and our premium, gold, and all our sponsors, as well as our media partners, we would like to thank them. Our Our institutional sponsors, so both those who have kindly provided funding to help make this meeting possible, and also those who have supported the conference by supporting all of you in coming here. And I would also like to thank all the partners of all types who have helped in any way, particularly our two major sponsors, Microsoft and Telefonica, because I think the connectivity has been really good. I haven't had, I think I'm the first person who hears, oh, well, the Wi-Fi is awful, and I haven't heard that. So, thank you. So, where next? The POC met last night. I think it was a record-breaking meeting. When the meeting finished, somebody said, oh, it's not today, it's tomorrow now. So we met to start planning the next year's conference. And in fact, next year's LOC have already been thinking about ADAS 28 for a good year already. So I would like to ask Peter Teuben, oh, there he is, from University of Maryland to come and tell you a little bit more about next year's ADAS.
That's the wrong laptop. Well, first I want to say that when I came here at this meeting, I came with different eyes and ears because I knew I didn't have much time to look at many things, but I looked at things like what's in the back, what's in the chairs, and so forth. Which one is it? That one? Yeah. And I don't think it's a surprise where the next year ADAS will be, right? It will be in Washington, D.C. Now, we're cheating a little bit because it's going to be in College Park, November 11 through 15. I think most of you have probably seen the table. And there was an information spec sheet with some ideas about themes that we could do. And that's, of course, will be decided on by the POC. We have an idea about a hackathon, including some people from the community, students, Google Summer of Coders, companion family program. We have lots of ideas. If you're not familiar with it, that's the area that we're in. We like to boast that we have the most astronomers in the world in a sort of concentrated area, but I didn't count, but there you see on the map all the various institutions, the AAS, AIU, NSF, NASA, they're all there. It's on the University of Maryland. There's a brand new hotel. University of Maryland is famous for a number of alumni. Here is one of them, or two of them. Google is well known that I don't think they were the dropouts, but they were maybe real graduates. The Oculus Rift people, Reben, for example, there's a new Reben Center being built, which I thought I had a picture of. Go back to that. It'll come in a second. So the Reben Center is right next to the hotel. Should be finished by next year, but I'm not sure if we can actually go inside of it. During the meeting, you may have also met 4 of our LOC people, and I was going to ask them to stand up. Yes? We also had there's Tom and Alice, Kim and Anne. We had a suggestion box form, which we all have in our hands, I think a few copies. If there's any of you who still have ideas that you thought you want to write down, themes, other ideas that we could implement next year, let us know. Raise your finger if you already have some. If you want a form, go to them, pick it up, give it to us after lunch. There is a bowl at the table, at the 2018 table, where you can enter those. That's the hotel. That's an artist's conception. The real one will come. It is there. It finished 2 months ago, but they call it a soft opening, so I don't know what that means. The conference center is all on one floor, which certainly helps Pepe now that his knee is really bad, so he doesn't have to walk the stairs. That's the real hotel. That's where we hope to see you next year. Thank you very much.
Thank you, Peter. Next, I would like to thank my colleagues on the Programme Organising Committee for their work on this year's programme, and in advance for their work on next year's conference, which will start in the next couple of months. So could I ask the POC to please stand? And we also thank you. So the makeup of the POC will change slightly for next year as some people rotate off and others come on. As I said at the start of the meeting, I encourage you to come and talk to us, to email us, to phone us, tell us what you liked about this conference, tell us what you hated about it, tell us how we can do better next year, because it's your conference and we want to make sure that next year's conference has in it what you want and what you need. So last but not least, by any stretch, I'd like to thank the people who've made this meeting happen, ADAS 28, the local organising committee. This has been headed by Jorge Ibsen, Maurizio Solar and Pascal Ballester, and they have organised the venue, the delicious food, maintain our connectivity to the outside world, brought a lot of support from government and industry, and done a huge number of things invisibly behind the scenes that have made sure that our sessions ran smoothly. They promised us an excellent conference, and I think they delivered. So thank you. So I'd like to invite Jorge up to say a few words on behalf of the LOC.
Just a few last announcements. I have been asked by Pascal to remind people, we managed to get all the copyright forms but 2. I'm not going to name them, so please, Martín Villanueva and Su Chiang Chen, please deliver the copyright form. Martín is waiting here for your signature. Don't leave without it. You won't be fit if you leave. No lunch, absolutely no lunch. And I'm not going to be, again, doing a long speech, but I have to say that this conference was organized by a quite big bunch of people, beginning from the LOG members. Some of them are here, like Monica, and I don't remember how many else we have. Mauricio and Pascal have been doing a lot of heavy lifting in many topics. So for the LOG, thank you very much, all my colleagues, but that's not enough. I would like to thank a few people by name. I'm sure I'm going to miss some names. First of all, I would like to thank the brand designer. He worked for almost 6 to 8 months to design the brand, and you saw the brand last year in Trieste. His name is Marcelo Moya, and he has been wonderful in keeping all the things consistent. I would like to thank Andrea Riquelme. I have to correct the number you gave, Nuria. She informed me today that the number of press releases that went out and we got final published is 145, including international press. I would like to thank Cesar Verdejo. He is the webmaster. He has putting up with me sending emails at very unholy hours, and he has been replying 5 seconds after. And that's the reason why you have a website is actually very active and was most of the time up to date. And I would like to thank Nicolas Lira from Alma EPO. He has been the person behind all the Facebook Live, all the social media, he has been the interface to the community in social media. He has been here the whole week. You haven't seen him because he has been busy in the newsroom. And finally, I would like to thank wholeheartedly the team in Conde Producciones. They did an amazing job. I would like them to stand up, please. And I will name you. I'm sorry, I'm going to shame you. I would like to thank Julieta Martinez, who has been leading this, Jimena Guayo, Marianela Poblete, Giovanna Villablanca, Paola Cadaveira, Macarena Steinmeier, Patricia Benitez, Maria Jose Diaz, all the personnel that you saw in secretary, all the additional design helpers, technicians, among others, and of course, also I would like to thank we had a number of students from Santa Maria University helping with the organization I don't have, but there were about 20 people helping. So thank you all. And I would like to give them an applause. I think they have been wonderful. And finally, I would like to invite Julieta to come to this place because we have a small gift for you. She has been the public face in all this tremendous coordination effort. Please stand up. So, thank you very much, Julieta. So, and I have been told that you can share the chocolates if you want. Por acá. Okay.
Gracias.
Gracias.
Thank you very much.
And that's all for my part. It has been a pleasure to have you here in Chile. I hope you have a wonderful time and you enjoy the country as much as I do.
Two more things, and then you can have your lunch. Posters, the best poster. Thank you, all of you who voted. And thank you, all of you who put up with me haranguing you about voting. So we have a tie. So well done to two posters, both of whom get 6 pages in the proceedings rather than 4. So the two posters are poster 90 by Roberto González, entitled Astro CV, a computer vision library for astronomy. Are you here? And the second, the other tied poster is poster 58 by Alessandra Zanichelli, a public data archive for the Italian radio telescopes. Are you here? So the editors will be in touch. They will know that you can put in 6 pages. Thank you. So all that remains for me to say is to wish you safe travels home, and we hope to see you in Washington, D.C. next year. Thank you very much.